Okay, I hope you all had a good Thanksgiving break. This is our final class, final lecture. So after this semester is over, you'll have a story that will astound whoever interviews you, that you designed a pipelined RISC CPU from scratch. We have our final exam on next Monday at 4 to 6:30, and it is comprehensive. I've got a practice exam with the solutions on Dropbox. It was the one I gave last year. Same material, but also I've got some additional practice questions from the textbook that I've picked out from Chapter 5 that cover specifically the new material we've had since we started talking about the digital building blocks. So those are all good questions. So between those and the practice final, it's a good study aid. Lab 5 is due on Saturday by 11:59 p.m. This coming Saturday, and that's also when the graduate/honors lab is due.
Has that been posted yet?
No, but I'm going to talk about it today. Charles, we don't have a PDF of it yet. We didn't do one last time.
I think last time you just did this and just explained.
Yeah, we just did it informally. Oh, you know what? I take that back. I do have a description. I do have a PDF for it. I'll post it tonight. But I will go over the details today. Okay. So last time we talked about ripple carry, carry look ahead, and prefix adders. So how do you take an adder and make it a subtractor? So you have an adder. So you can add two values, but if you want to subtract them, you can convert b to a negative value, negate b. And then, so how do you do that? You convert b's to b, you take the 2's complement of b. So that's like saying not b plus 1, where not b is a 1's complement. That's where you take the complement of each of the bits in b, and then you add 1. Make sense? Now, when I used to see this, I used to say, well, wait a minute, that requires 2 adders. But it doesn't, because you can take advantage of the carry in input on the adder. So it's kind of like regrouping these. So it's a plus b, and then add 1 through the carry in. This symbol is meant to show a hardwired 1. VD, that's a VDD symbol. Make sense? So you can do this, you can regroup these because the addition is associative. But actually, you're not really even doing that technically, because it's not like you're adding A and not B and then adding 1. The adding 1 is part of the adder itself, right? So there's not really any kind of ordering there. Does that make sense? Okay, so this is something that we actually did in your CPU design, but this was part of the ALU code that we gave you. How about comparing two values? Well, if you want to compare for quality, one way to do that is to use the XNOR. XNOR is a comparison, is a bitwise comparison operation, right? So if XOR is true whenever one of the inputs is 1 and the other one is 0, right? If it's a two input XOR, right? If there's more than 2 inputs, then it's like a parity operation, right? But if you take the 2 input XOR of each of the corresponding bits and two multi-bit values, then it will give you there'll be a 1 in all the bit positions where they differ. But if you use XNOR, then you'll have a 1 in all the bit positions where they're similar. You guys with me on that? Right? So for example, if you have A and B and they're 4-bit values, right? If you do an XNOR here, then that'll be 0 XNOR 1 is a 0. And then 1 XNOR 1 is a 1, and 0 XNOR 0 is a 1, right? So in this case, this is indicating that the 3 most significant bits match, right? But then if you feed all of these into a reduction operation, remember in Verilog you can do a reduction where you take all the bits of a multi-bit signal and you feed them all into like a big gate. In this case, they're all going into an AND gate. Then, obviously, if you ANDed all these bits, you'd get a 0. But if these did match, if this was a 0, then you'd have all 1s here. In which case, if you ANDed all these, you'd get a 1. Right? Does it make sense? So it gives you a 1 if all the bits are equal between A and B. Make sense? Okay. What about checking to see if one value is less than another? If A is less than B, you just subtract, and then you check the sign bit of the result. Now, when I was going over these slides today, that actually surprised me a little bit because I don't know if you guys looked at the ALU design that we gave you. But it also had an operation for A less than B. And this is the code for that. And it was a little bit more complicated. It checked the sign bits of A and B individually. So it initialized low to be 0. And the idea is that if A is less than B, low should be 1. So the initial value of low is 0. And so this is the opcode, the ALU opcode for set on less than, which is the A less than B operation, 1100. And so if the sign bit of A is 1 and the sign bit of B is 0, it means that A is negative and B is either positive or it's 0, right? Then low would of course be asserted, right? Because any negative number is going to be less than a 0 or a positive number. But then if that is not the case, meaning that they're both negative or they're both positive, or if A is positive or 0 and B is negative, right? Which would be the other 3 cases. Then it looks at the sign bit of diff, right? Which is what this is doing here. Right, this is looking at the sign bit of diff. So this is a difference, and that's bit n minus 1. That's the sign bit. Make sense? So the question is, which one's right? I mean, is this? Could I get away with this, just this design, or do I have to do the more complicated version that we gave you in class for the ALU? Well, we got to figure that out. We could look at some examples. Some test cases. So let's say diff sign and A less than B. Okay, so let's say A is -5. Let's say they're both negative. A is -5, B is -4. So A is less than B, should be. Right? But if you subtract them, that's going to be 5 minus -4, right? So the diff sign is going to be negative, right? So turns out that That works, right? Makes sense? But if they're both negative and you've got -4 and -5 here, this would be 4 minus -5, so the result there would be 1, which would be positive, or 0 sign bit, which means the result is positive or 0, and that should be a 0, so that works out. Same thing if you've got 5 and 4. 5 minus 4 is positive. Result there should be a 0, whereas if you had 4 and 5, you'd have a negative sign there, and the result should be 1, right? So even if the signs match between A and B, that circuit will work. Make sense? Well, what happens if, what was the other case there? What happens if the signs are different? Let's say you've got -5 and +4, right? So this was the special case, rather, that we were testing in the ALU Design in class. This would be -5 minus 4. Obviously, would be a negative, and so A is less than B, right? And then if you have 5 and -4 here, then 5 minus -4 is going to give you 9. And A is not less than B, right? So seems like it works, right? Guys with me? Right? So yeah, this actually works. I didn't need to make it this complicated. We didn't need this if statement. I'm not sure why it took. See, the first time I used this design was in 1999, 2000. So it only took 19 years for me to figure this out. That this is a redundant if statement. Literally, it took me 19 years to figure that out. Yeah, in fact, even this part's redundant. The only thing I need is the sign bit of the difference, as indicated there by the book's design. Okay, shifters. So we made a shifter. We use the shifter operator in Verilog, and we let the synthesizer decide how to synthesize that into a shifter circuit. This is how a shifter circuit could potentially look, though. The idea is that this shifts by to the right. So there's a 2-bit shift amount, so that allows us to shift by 0 bits, 1 bit, 2 bits, or 3 bits. And so we've got a mux controlling each output bit, right? And so the mux that sets the most significant bit of the result has 3 of its inputs are hardwired to ground. That's the ground symbol, that's hardwired to 0. Because if you shift this value by anything other than 0, then the most significant bit of the result is going to have the 0 shifted in, right? So that mux will bring in a 0, right? If you shift by 0 bits, then it's just going to pass A3 to Y3, right? But if you shift by 1, 2, or 3, and of course the shift amount is the select, right? So if the shift amount is 1, 2, or 3, then we're going to put a 0 out because we'll have shifted that into the most significant position on the result. For Y2, the same thing applies for shift amounts of shift amounts of 2 or 3. But if you shift by 0, you pass in A2 directly out to Y3. And if you shift by 1, then they're picking up A3. See that? So A3, which is the leftmost bit of the input, will get shifted down to bit 2 of the output if the shift amount is 1. Right? If the shift amount is 2 or 3, then you're going to be shifting into 0. And then y1 is going to have is going to be 0 if the shift amount is 3. But if the shift amount is 0, then it's going to be a1. If the shift amount is 1, you're going to get a2 coming out to y1. And if the shift amount is 2, then you're going to have a3 going to y1. Make sense? So this is a barrel shifter design. And these are actually quite expensive in terms of hardware resources. Some embedded CPUs don't offer a barrel shifter. In the FPGA tools that we use in 313, or that we used to use in 313, there was an option for the CPU that you would, the soft core CPU that you put on the FPGA. There's an option to turn on or turn off the barrel shifter because there's a lot of hardware. If it's a 32-bit shifter, then you have to put, obviously each one of these muxes has to be a 32 to 1 mux, right? And then you have to have 32 of them. So that's a lot of hardware. So if you don't plan on doing any shifts, then you could do the, then you can not have that shift hardware in there. You guys make sense? With me? Okay. There's also this idea of a shift register, which is where you have D flip-flops that are connected in series. So you have one D flip-flop feeds into the input of the next one in like a line. And so I used to, when I first saw this, I was confused. I was like, wait a second, hold on. If you have a circuit like this and there's a clock edge, that clock edge is going to cause all these guys to clock. But if the first one feeds its input through really fast, it's going to immediately get into the second one, and the data is just going to race through it really fast on one clock edge. But in practice, these D flip-flops, the propagation delay is usually very safely outside the bounds of the aperture time, which is, remember, the aperture time is the time around the clock edge when you're actually sampling the data into these, right? So what ends up happening is when the clock edge happens, the data in these flip-flops only shifts down by one position at a time. So in other words, these flip-flops will do a shift by 1 bit every clock cycle, right? So it'll just continuously shift data down. Yes?
So in theory, if you slowed the clock down far enough, would it have the potential to propagate more than one, or?
You'd have to. No, it would be these are edge triggered, so you'd have to make the edge. You'd have to extend the rise time of the clock. So you'd have to, instead of the rise time. See, normally the rise time is like 1/10 of the clock period or less.
Oh, okay.
You'd have to make the rise time.
Stupid long.
Yeah.
To make that happen.
Well, sorry. The rise time. It's actually I take that back. The rise time is not relative to the clock period, but usually you see it about 1/10. But if you were to extend the clock period, the rise time wouldn't extend with it proportionally, right? So, yeah, if you
so if the rise time was a gradual slope versus just like a cliff jumping straight up,
right,
then you could have issues.
Yeah.
Okay.
Yeah, you would end up violating timing.
Okay.
Timing constraints. But yeah, so this, if you set up shift, we used to have Charles, did we still give them the code for the, I forget, did we give them the code at the beginning for the DE2 board that did the shift register?
Yeah, that was for the bouncing thing.
Yeah, the bouncing light. Yeah, except that was in Verilog, so it wasn't a direct, you don't directly connect the D flip-flops in series, because this is what would get synthesized from doing the shift by 1 operation in Verilog. You guys with me? Okay, so in this case, you would have to, this S in would be the bit you'd shift in, so you'd have to be shifting 1 bit at a time. And actually, this is how you configure FPGAs, by the way. FPGAs get configured 1 bit at a time. An FPGA is a giant shift register. So when you configure the FPGA, I don't know if you guys noticed this or were annoyed by this, but when you configure the FPGA, it takes like 20 to 30 seconds. And you're like, I mean, the configuration file isn't really all that huge. Shouldn't take that long. But yeah, you're shifting in. JTAG makes a big shift register. In the case of an FPGA, you have to shift in a lot of bits. You have to fill up every LUT and every switch and all the muxes that are inside the LEs, the logic elements. So there's a lot of bits to shift in. Okay. Also, JTAG works at a slow clock rate too. It's like 1 megahertz. But you can also set up a shift register where you load it in parallel. So if you add a mux before each one of these D flip-flops, one of the inputs on the mux will carry forward the previous D flip-flop in the line, but the other input will be a parallel load. So this is how you would create a parallel to serial converter, for instance. Like if you wanted to be able to put a parallel word in and then shift out one bit at a time. You would build it this way. Does that make sense? I don't think I explained that very well. But you've got a D flip-flop, and you've got a mux, a 2-to-1 mux, feeding each one in. So if these muxes selects are set to 0, sorry, if they're set, if they're set to 0, then it acts like a regular shift register. Each output of each D flip-flop feeds into the input of another, right? If you set the muxes to 1, then instead of these D flip-flops shifting on the clock, they'll load on the clock, where all these, you can provide a parallel load coming in to the one input on each of these muxes. Right? Now notice they also have this, these Q zeros also allow you to do a parallel readout as well. So in this case, they've got it where you can load it in parallel, you can read it in parallel, but you can also shift it out serially. Guys, it makes sense? All right. Okay, so shifters, what do we use shifters for? Shifting is a fundamental bit manipulation operation. It's also forms it's the way that you build multiply and divide operations. So if you shift to the left, you multiply the value that you're shifting by 2 raised to the n power, where n is the number of bits you shifted, right? Do you guys cover this in 212? Probably talked about this before. So if you have a number and so if you have 5 in binary, if I shift it 1 bit to the left, obviously I shift in a 0 in that right-hand position. That becomes 10, right? And that's going to be 5 times 2 to the 0th power. If I take that original 5 and I shift it by 2 bits to the left, I get 1 0 1 0 0, right? Now this is bit 0, bit 1, bit 2, bit 3, bit 4. So this is 2 to the 4th power. So this is 16, right? Plus 2 to the 2nd power is 4. So this is 20. And this is going to be 5 times 2 to the 1st power. And then if I shift it by 2 bits, 1 0 1, by 3 bits, 0 0 0, this is going to be 2 to the 5th power, which is 32, plus 2 to the 2 to the 3rd power, 0 1 2 3, right, which is 8, right? So this brings us to 40, which is 5 times 2 to the 2nd power. 5 times.
Number of shifts, so it should be 1.
Sorry,
3.
yeah, sorry, 1 2 3. I had this wrong. Yes, thank you. 1 2 3. Gotcha. Yep. Thank you. Make sense? Divide works the same way or a similar way. You have a number. Let's have a bigger number instead of 5. Let's do. Let's Let's do 1, 1, 0, 1, which is 13. Okay, now if I shift this to the right by 1 bit, I will, in this case, I'll do a logical shift, because I'll assume this is an unsigned number. So I'll have a 0, I'll shift in a 0, and I'll get a 1, 1, 0, right? Which is a 6. Which is 13 divided by 2, but you round down. And the reason you round down is because you lost that 1 bit there, right? That would have been, that represented the 0.5. That would have normally been shifted to the right of the decimal point, but if we don't have a bit position there, it gets shifted off, it just gets dropped, right? If we don't have any fractional bits. Make sense? If you shift it by 2, so this would be 0, 0, 1, 1. It divides by, so this would be 13 divided by 2 to the first. This would be 13 divided by 2 to the second. 3. 13 divided by 4. Right? If we shift again, we get 1, which is going to be 13 divided by 2 to the third. 13 divided by 8 gives you 1. Right? Okay, so we can shift to the left to multiply, and we can shift to the right to divide, but we're limited to powers of 2. What happens if we don't want to be limited to powers of 2? How do we deal with that? So if we want to create an arbitrary multiplier, multiply any 2 numbers, not just one number by a power of 2. So let's say I want to multiply, let's see, 3, I want to multiply it by 5. So we're going to call the first number there the multiplicand, and the second number the multiplier. And it doesn't matter which one we assign to which label, because multiplication is commutative. So this 3, we can shift it and multiply it by a power of 2, but then we can do that for multiple powers of 2 as represented by the 1 bits that are in the multiplier. So the multiplier being 5 is like shifting it, is like multiplying by 4, right? And multiplying it by 1, and then adding those two as partial sums, right? So this, actually so this 1 bit here is in bit position 0 of the multiplier, right? So this means I want to shift by 0 bits, because the 0 bit is turned on in the multiplier, and the 2 bit is turned on in the multiplier, right? So I can take that 3. So I could take that 3 and not shift it. So it's 3. And then I can shift it by 2 bits, right? Which would shift in 2 bits on the right-hand side, because I'm multiplying, so I'm shifting to the left, right? And then I can add those 2 up, and I get 15, which is 3 times 5. All right, so these become partial sums. Each partial sum is just a version of the multiplicand shifted a number of bits corresponding to each of the 1 bits in the multiplier, right? And this actually matches up to the kind of the grade school procedure you use, where you take the multiplicand and you multiply it by the first digit on the right of the multiplier, and then the second digit, which would just be 0, right? Because we're taking that and multiplying it by 0. But you have to shift it over, right, by 1 bit. And then you take the multiplicand and go to the next digit there, the digit 2, which would be 1, 1, 0, 0, and then 0, 0, 0, 0, and you add all these guys up, and you still end up with 15, right? But see, in my case, I just went straight for the, the 1 bits that were set, and I just used those as shift amounts. Make sense? So the hardware for this could actually be set up as an array of full adders. Is it like a 2D array of full adders? Now this is a little confusing because this diagram is showing the full adders as adder symbols. Adder symbols, this shape, right? But I think earlier it doesn't do that, right? Oh, it does. Yeah. Okay. Sorry. Yeah. I take that back. The book's consistent here. It always shows an adder, even if it's a 1-bit adder. It shows it as this symbol. So with the multiplier, you can take each bit of A, which is the multiplicand. B is the multiplier, right? And so because B is the multiplier, notice that B is being used to gate the first stage of A. When I say gate, it's like putting them into an AND gate. So, an AND gate is kind of like a 1-bit multiply. Make sense? So they take A0, let's see, let's be, the A0, A1, A2, A3, and they put these AND gates, which they AND with each of the corresponding bits of B. So A0 gets ANDed with B0 here. And that becomes the least significant bit of the product, right? You might say, well, that doesn't go through an adder. Well, no, because actually that bit drops straight through to the result, right? So the least significant bit of the product is just depending on the least significant bit of the two operands, right? But then when you get to the next bit over, the next bit, the bit 1 of the product, is the sum of A1 B0 and A0 B1, right? So they take A1 and B0 and A0 and B1, and they put those into a full adder, right? Which is doing this addition, producing a single bit output. Make sense? Now, do you need to carry out from that? Yeah, because you could have carries here. When you add these partial products up, you can have carries, right? So notice that there's a carry out that goes into the carry in of this adder, and this adder is adding up bit 2 of A, bit 0 of B, bit 1 of A, and bit 1 of B, right? Now wait a second, look at that. There's actually a third thing you have to add there. There's a third thing in that column, which is why they have to put another adder below that. So you've got 2 full adders now in series in order to produce the bit 2 of the product. Make sense? The next bit is going to have 3 adders in parallel, because you can see here there's 4 things you have to add, so you need 3 adders to add 4 things, 4 bits together. With me? Make sense? So this circuit lines up with the, just adding up the partial products where, B is the thing that's controlling whether or not you're adding a shifted version of A together to form a sum of partial products. So over here we've got A bit 3 that we add to 0. Why do we add that to 0? Well, it's because we still have to bring in the carryout of the previous bit. Now, they could have used a half adder here, right? This is a little, right? They could have used a half adder because a half adder would have been just had A and B and not the carry in, and so they wouldn't have had to put a 0 in here. But they used a full adder, so this one of the inputs is a 0, but they're still adding 2 bits together to produce a single bit output. And then they still have to have a carry out that carries out from, let's see, A3. So they still have to have a carry out that carries out from this column to this column. Make sense? Okay. Now, the problem with this design, though, as you might imagine, is the more bits you add, the more full adders you have to go through vertically. And thus the propagation delay increases with the number of, directly proportionally to the number of bits, right? But you can solve that by creating an adder tree. And this actually isn't in the textbook. This is from the Hennessy and Patterson textbook. But this is an optimization where instead of doing, this is what the book for this class is showing, this style. But you can rearrange those adders and you can build it as a tree, and then it's just a log base 2 number of adders you have to go through. But I just thought I'd show that. It's not not that important, right? You don't have to know that for the final. Okay, how about division? How's division work? Okay, let's say we want to divide 131101. We want to divide that by 3. So 13 is the dividend, and 3 is the divisor. And the answer is the quotient in the remainder, right? The dividend is the numerator. The divisor is the denominator, right? So this is 13. This is going to be 13 divided by 3, or 13 over 3. Right? So how do we do this with? Well, what's in our toolbox at this point? What can we use? Well, what have we shown so far? Shifters and adders, subtractors, right? This chapter is sort of building from the bottom up, right? So we can shift and we can add and subtract. So now we want to do divide with that. Well, one way to do this is to take the divisor and shift it to the left. So this would be 3. Shift to the left by 1, get 6. Shift to the left by 2, get 12. Shift to the left by 3, get 24. Right? And once you've got those, the idea is to figure out, so this is shift by, this is, what is this, 3, shift left by 1, 3, shift left by, sorry, this is 0, so I screwed that up again. That's shifting by 0, that's shifting by 1, shifting by 2, and shifting by 3. So the idea is to figure out how many of these shifted versions of the divisor we can subtract out of that number, starting from the largest one. So can we subtract 24, without it being a negative result? No. Can we subtract 12? Yes, right? So that means that bit 2 of the quotient is going to be turned on. And then what do we have left? We have 1 is the remainder from that. So can we subtract 6 from 1? No. Can we subtract 3 from 1? No. So we're left with a quotient where the only bit that's set is 2. Right? But we still have 1 left over. That's the remainder. So the quotient's 2, the remainder is 1. Does that make sense? Come up with a better example here. Let's do a less trivial example here. So let's say we want to divide 3 into 51, right? So let's do the same thing again. We have 3, so 3 shifted by 0 is 3. 3 shifted by 1 is 6. 3 shifted by 2 is 12. 3 shifted by 3 is 24. 3 shifted by 4 is 48. 3 shifted by 5 is going to be 96. Okay, so we start out with 51. We see if we can subtract 96. We can't. Can we subtract 48? Yes, that means that bit position 4 of the quotient will be set to 1, except that 51, we're going to take out 48. All right, so we got 3 left, 3 left, right? Can we subtract 24 from 3? No. Can we subtract 12, 6? Oh, we can subtract 3, which will make that then, we'll subtract 3, get 0, and we'll set bit 0. So bit 4 and bit 0 are going to be set to 1, right? So 4, so that's, 0, 1. Right, there we go. So that's bit 0, bit 1, bit 2, bit 3, bit 4. So bit 0 and bit 4 are both set, which means that this is, 2 to the 4th plus 2 to the 0th, right? Which is 17, right? It turns out that 51 divided by 3 is 17, with the 0 remainder, right? So what's the point of this? Well, basically, you're taking the quotient and you're shifting it to the left. You're trying to subtract that value from the dividend. If the result of that subtraction is negative, then you restore the dividend back to what it was before you subtracted it. If it's not negative, you just leave it the way it is. Then you shift the value over to if you start out with this shifted left. So if I started out with this being 96, then I would keep shifting this value down and attempting to subtract it from the current value in the quotient, the dividend register. You guys with me? Does that make sense? Now another way you can do this, instead of shifting the divisor to the left, you could also take the dividend and shift it to the right instead, because it doesn't make any difference. You can shift this guy to the right, or you can shift this guy to the left. Either way, it's equivalent, right? So in this case, I was taking the divisor and shifting it to the left, making it a bigger number, and trying to subtract it out of this, right? You could do it the other way. In fact, the other way is kind of the grade school method. So let's look at it doing it the opposite way. If I took 3 and I divided it by 51, which is, 51 divided by 2 is 20. 25 with a remainder of 1, right? 25 divided by 2 is 12 with a remainder of 1. Then we get 6. 3, and 1. So 1, 1, 0, 0, 1, 1. It's 51. Right? 1, 1, 0, 0, 1, 1. So the way you would do this, like kind of like in grade school, is that you would look for, you would see, well, this 1, 1 can be subtracted from that 1, 1, right? And the corresponding quotient could go above there. So I could subtract 1, 1 and put a 1 there, right? And then I would subtract that and get a 0, right? And then I would carry down that 0, and I'd have a 0, which I can't divide 1, 1 into 0, 0, so I would put a 0 there. I drop down this other 0, same thing. I drop down that 1, same thing. Then I drop down that 1, and then I'd have a 1. Right? It's kind of like this, how you do it in grade school. But see, the problem is that this relies on, you kind of seeing, lining things up, kind of visually. If you design a circuit to do this, it has to actually subtract every possibility and then do the restoration if the result is negative. You guys with me? Right? So the way a circuit would do it would be 1, 1, what was it again? Crap. 0, 0, 0, 1, right? 0, 1, 2, 3, 4, 5, 32 plus 16 plus 1, 40, 48. One more 1? Wait, no, that can't be right. It's 48. And what was it again? 50. What I use 51? Yeah, that's right. 51, 48 plus 3. Yeah, that's right. Okay, got it. Okay, so I mentioned you could take the divisor and you can shift it to the left and subtract it from this. Or you could take this and shift it to the right. It's up to you. So let's just imagine that we shifted this guy all the way to the right to where we kind of get rid of all these bits. So we just have a 1, right? So we're going to try to subtract 1 minus 3, right? We're going to get a negative value there, negative 2. So then we'll have to restore this 1 back to 1 and put a 0 there as the first bit of the quotient. Then we're going to drop down this 1, do the subtraction, get a 0, put a 1 there, right? Then because that subtraction gave us a 0, right? Then we don't restore. We don't restore the original value. We just leave it at 0. But then we continue to shift in bits from the original quotient. So shift in a 0, shift in a 0, shift in a 1, shift in. Meanwhile, we're putting zeros up here until we finally get to the point where we have a value we can subtract without having to restore. Does that make sense? So basically, to kind of summarize it, you either take the divisor and you shift it left and you keep trying to subtract it, right, while from the original dividend, or you take the dividend and you shift it to the right and you try to subtract from that the divisor. If the result is negative, you restore it, and then you keep shifting bits in to the left. So the circuit so basically the problem here is that you've got this data dependency, because you have to try this subtraction, and if by subtracting, typically this dividend goes into a register that's usually called the remainder register, right? Because what you have left over at the end after everything is done with is the remainder, right? So you have this remainder register, and you initialize that with usually the least significant bit of the original quotient, but the other bits are still in there. They're ready to be shifted in to the right-hand side as you shift that remainder register to the left, right? So you keep shifting that to the left each time, and you just try to subtract the divisor from that, and if the result is negative, you restore it. But see, that's the problem, is that If it's negative, you restore it. That creates a data dependency. And that's why dividers tend to be slow, because you have to go through the process of subtracting and restoring, conditionally restoring. Does that make sense? So the book has this design, which is kind of neat. I've never seen this one before. This is actually a combinational circuit where the data flows in from the beginning, from the top, and works its way down. So you've got A and B. B in this case is the divisor, and A is the dividend. And you take the dividend and you start it off by shifting it all the way down to the right, where only the most significant bit is available with 0. So you got 0, 0, 0, A3. Make sense? So that's the same thing I did here. When I subtracted this 3 from that 1, essentially the subtractor was only seeing the most significant bit of the dividend. You guys follow that? Right? These other bits were hidden, right? So I just had a 1 for all, the subtractor was just seeing a 1. So these boxes are actually full adders. So they're taking B, right, the divisor, that would be the 3 in that example, and they're doing a 2's complement. See, they're negating B, not B, not B, not B, not B, and they're sending a carry in, right? So that's the 2's complement. So they're taking the 2's complement of B, so they're negating the divisor, and the dividend is essentially shifted 3 bits to the right. So the only thing you see there, you got 0, 0, 0, A3. So then they subtract. Well, they add, but they're adding the 2's complement, so they're subtracting B. And they're taking the carry out of the most significant adder, and that's the quotient bit. What's that all about? Well, I don't know if you guys, if you looked at the ALU design that we gave you for your CPU when we did the set less than unsigned, we actually used the carryout to determine whether once you subtracted A minus B, you got diff, right? We looked at the carryout to determine if the result of that was negative. You remember that? No, you might have not looked at it. So if you do a subtract and the carryout is 0, then that means you got a negative number in the result. So if you negate, if you complement that, this is saying that you're getting a non-negative result. So that would mean that when you subtracted the shifted dividend, when you subtracted the divisor from the shifted dividend, you got a positive or 0. Does that make sense? It's actually not. That first subtract, by the way, it's impossible for there to be anything other than a 0 there. Because the only way that first subtract would have worked out for us is if you divide by 1. Right? Any number bigger than 1 is going to fail on that first subtract. It's guaranteed. But if you divide 15 by 1, then you'll have a 1 there. And so your first quotient bit will be a 1, right? So the only way that this thing will ever be true is if you divide by 1, right? But they have to account for that, right? In most cases, that first quotient bit will be 0, right? Does that make sense? Okay? So then they take the result. Now the result of that are these bits coming out of these guys. And that's going to be the new remainder value, which may or may not be negative. If it's negative, they have to restore it back to the original form. And that's why they use boxes here, because inside this box, they have this pseudocode. And basically what this is saying is that if the result is less than 0, then they restore the original value that's coming in, which is, let's see, they've got R. So the output of this is R. Let's see, R prime, which is the new remainder value, right? And they have an input R, right, which is A, right? So the first input is the original value of the remainder register, right? And so if the result of that were negative, then they restore, this is where they restore the original input to the output. Does that make sense? So that actually happens here. I don't know. If D, which is the R minus B, if that's less than 0, then the output is, well, Q, that's this output. So I'm sorry, that's not actually the carry out. That's this Q output, which actually is going to be equivalent to carry out, I believe. But that's Q0, which is the quotient, right? So if you got a negative value, then you put a 0 in the quotient register, and you restore the original value that came in. Otherwise, you take D and you output that as the output, right? Which is the new remainder value. That's the new value that's in your remainder register. Anyone follow this?
This is the one where it just keeps subtracting until it goes less than 0. And
Yeah.
then bumps it back and says we're done.
Yeah, basically, but it does it at each stage, right? So you've got
It doesn't check it every stage.
right, yeah. So the equivalent. So if we go back to here, the equivalency here is if we do the same example again, the 3 and the 51. 0, 1, 2, 3, 4, 5. Yeah. So the output of this first stage, right, will be the result of taking 1, right, because that's A, that's 1, just the most significant bit of the dividend, right, and you're going to subtract the quotient, which is B, right, and that's why you have, the reason why it's not B with a carrying of 1 is implementing the subtract. Right? And you're going to get a negative, this is going to be -2. Right? So this -2 has to be restored back to 1 because it was negative. And then the first quotient bit is 0. So that's what's happening here. After that first stage, quotient 3 is going to become 0. Well, actually, is this 3 bits? No, this would actually be 0, 1, 2, 3, 4, 5. So this is actually a 6-bit. This is showing 4 bits. So this is a 6-bit example. This is a 4-bit example. So these boxes are basically comprised of a full adder, which is what's shown here. It's a full adder where you've got R and B. Initially R is 1, right? And then if I subtract and it's negative, then R will become 3, and then R will become 6, and then R will become 12, right, as I shift in values, right? Or alternatively, it may be the difference if the subtraction is successful, if I'm able to subtract and get a non-zero value. So, and then this mux is what's doing is taking care of the restoring process, where it's taking R, which, you know, remember R is the first input, that's the quotient or the remainder, what will eventually be the remainder. That this mux is restoring the original value of that if this D is negative. Yes.
So, on the first adder, you've got an input that goes all the way to Q3, but then you also have the same one on the very last adder. Why not just make it one input, like if it's the same one?
So you're talking about this adder, this block?
Yeah, that one, and then like the very last one, if you consider it, like on the same row. So if you look at the
Oh, this one?
Yeah.
Oh, yeah. That's a good question. Yeah, that's a good question. You're talking about this. Why is this wire here?
Yeah.
Right. Let's see. That wire is, so the outputs here are R prime, right? Which is so basically every time you add, you do this shift, right? So that's one of the outputs, which is one of the R prime outputs. And the other output is, trying to remember here. Oh, is it the carryout? That's the carryout. Is it the carryout? R prime is the single bit output. Yeah, and we've got the carryout there, right? Yeah, so that must be the carryout. And then the third output is, I don't know what the third output is. But I mean, what's really happening there is you're just controlling whether, they have Q as an output here, right? Which is just, it's setting Q to be 0 or 1 depending on whether the subtraction was successful, right? Does it make sense? So the question is, what do we need to know to, who's telling us that? Who's going to notify us of that? Well, in this algorithm, they're just doing it in this line of code, right? But this is considering, this algorithm is for all the bits, right? They're not decomposing this into bits, right? So the question is, what do you need to know if the result is negative or not? Do you need the information from the least significant column and the most significant column? Yeah, oh yeah, well so one of the simplifications here is that notice I just wrote -2, right? But what would what would that actually be? It would be the 2's complement of 2, and it would be represented as a 6-bit number, right, in this case. So it would be, 1, 2, 3, 4, 5. So it would actually be that in reality, right? Because all these registers would be 6 bits. Make sense? So the question is, how do I know this is negative? Well, a sign bit, right? So would I need to know something from this column? They're showing information from that column. I don't think so. If I add 2 numbers, I'm subtracting 2 numbers, but I'm doing it as an add. I want to know if the result of that is a negative number. You use the carryout. You can use the carryout to determine that. The problem is you have to be careful you don't run into the bug that we had in the ALU that you guys were supposed to discover, right? Where that method doesn't work if the second value is 0. Right? So that might be what they're doing there. That might be a check. But yeah, that's a good question. I don't know off the top of my head. Why they have that wire there. But the problem is we need to know if the value is negative. So, but this is an unsigned divider. So looking at the sign bit isn't necessarily going to be enough. Doing the add, the carryout here would be a 0. Right? You say, how do you know that? Well, what happened here? We took a 1, 2, 3, 4, 5, 6, and we added that to the 2's complement of 3, which would be in 6 bits. So the 2's complement of 3 would be -1 would be all 1s, -2 would be a 0 there, so that would be the 2's complement of 3 and 6 bits, right? Because if I take the 2's complement again, I'd have 0, 0, 0, 0, 1, 0, I had 1, I'd have 1, 1, that would be 3, right? You guys agree? So if I add these up, that would be a 0 with a carry, a 1, a 1, 1, 1, 1, with a carry out of 0, right? So when I do this operation, I'd have a carry out of 0. Now, if I had subtracted and it worked out for me, like for example, if I subtracted 1 and I subtracted 1 from that, the 2's complement of 1 would be all 1s, right? So I would add that, I'd have a 0 carry, 0 carry, 0 carry, 0 carry, 0 carry. 1, 2, 3, 4. Yeah, 0 carry, but I'd have a carry at the end, right? So I'd have a carry out, in which case I knew that I had a 0 result or a non-negative result, right? That makes sense? Right? Now, what's the pitfall there? The pitfall is if you subtract 0. If you subtract 0, 1, 2, 3, 4, 5, 6. So if I subtract 0, the 2's complement of 0 is 0, and so I'd have a carry out of 0, and then I would be fooled, thinking, oh, I had a negative result because my carry out was 0. But in reality, no, it was actually okay. Right? So that was the bug on you guys. How many of you guys found that, by the way? Good. About half? Yeah, that was the bug, because the bug didn't consider the special case of comparing an unsigned number to 0. If you compared any unsigned number to 0, it would fool the ALU into thinking that that the number was 0. So how do you get around that? You have to check to see if the second value is 0. In unsigned numbers, no value is less than 0. So that has to be treated as a special case. So that might be what they're doing there. Yes?
You could also have extended diff to 33 bits instead of 32, and then you need the extra bit. I put it in my write-up.
Well, diff was 33 bits. That's how we captured this.
You added 32, and that truncated, and then you extended. You have to extend first and then add.
Oh, okay.
You never truncate.
Okay. I never tried that. It worked? But anyway, in this case, that might be what they're trying to do. They're trying to capture that. They're trying to capture whether you got a negative result, but they still have. But they're also trying to decompose it into multiple into columns. And then these 45-degree angle connections are the way that they're shifting. They're gradually shifting in A. So A was initially A bit 3 is the least significant bit. In the next stage, they're going to take that, they're going to shift it to the left by 1, right? And they're going to shift in A2, right? But they're not shifting A3 in necessarily, because this might have been the remainder, right? So they're shifting the remainder over, and they're shifting in each bit of the A value, the dividend value. Any questions about that? Any other questions? This is the dividers are tricky, which is, and they're expensive, which is why they're oftentimes you don't have hardware divide. Okay, well, good. So the last topic is memory arrays, and this one's pretty simple, because a lot of this you already know from having built your instruction memory. Memory arrays are laid out as a two-dimensional array of bits. There's columns, which represent the width of the memory, and the rows are the depth. Typically, each row is a different address, right? So every address gives you the number of bits matching the width, right? So for example, if you have this is a 4 by 3, right? So the number of rows matches up to the address, which is going to be a power of 2, right? But the width can be anything, right? The width doesn't have to be a power of 2. So this is why here you've got a 4 by 3 memory, right? Which is going to be 12 total bits stored in that array. This is actually the way memories are physically laid out on a chip. They're laid out as this 2D array of bits. And the reason for that is because whether you have a DRAM or an SRAM, it doesn't matter. Both of them have this notion of a word line and a bit line. The word lines are these wires that are laid out horizontally that are used to activate a word, which would be a row in the RAM. The bit line is they go vertically, and they are how you read out the bits from that row. They're also how you write bits into that row as well. So they're like bidirectional. That makes sense? So, for example, if you activate the word line here and there's a stored bit 0 in that entry, then it's going to set its corresponding bit line to 0. But if the word line is 0, the bit line is set to high impedance Z. It disconnects this connection here, right? So all of the rows are all connected to all the bit lines, but only one row is activated by its corresponding word line at a time, right? Otherwise, you'll have multiple rows driving the same wires here, the bit wires, right? So the word lines then are just connected to a decoder. So the memory address goes into a decoder, and then that address, which is a binary value, it essentially gets converted into a one-hot, or some people call them a unary value, where you have a bunch of bits that come out and only one of them is hot, only one of them is 1, that represents one of the physical word lines in there. And then, so that address activates one of the rows of the memory, one of the entries of the memory, and then the bit lines will then provide the data as the output, but it also allows you to drive bits into the bit lines to set a new value inside that row as well. So the way that works depends on whether you're talking about DRAM or SRAM, the two main, the most common memory technologies. With DRAM, each bit is just one capacitor. So what that means is that when the word line comes on for a row, that capacitor is being connected to the bit line through a single transistor that acts like a switch that turns it on. And so that capacitor, if there was a charge in that capacitor, that's a 1. So that's a 1 in that bit, and that 1 gets sent out to the bit line. Of course, you destroy it you discharge it in the process, so it goes away. You have to replace it afterwards. You have to recharge it after you get done with that. Make sense? SRAM is similar, except in SRAM it doesn't have a capacitor. It has two inverters. This is kind of cool the way this works. It's two inverters that are cross-coupled. So what happens is that you put a bit in here, and then if you put like a 0 here, the 0 gets inverted, becomes a 1, which then gets inverted again and becomes a 0. So these inverters, because there's an even number of them, and they're connected in a ring, they feed each other continuously, forever, in a cycle, in a combinatorial loop, right? But you can inject a new value in there, because if you drive another value in there hard enough, you can set it from 0 to 1 or 1 to 0. And the way that's done is through the bit line. So the bit lines come in, and you have 2 transistors there because you have to put in the value on both sides. You have to connect both sides or open up both sides of the loop. But then the bit line here is you've got the inverted and the non-inverted version, because obviously when you have a cross-coupled inverter, you always have a 1 on one side and a 0 on the other side, right? And the state of that cell will, be 1, 0 or 0, 1, right? You guys with me? So reading this out is really simple. If you want to set a new value in there, you have to drive a new value in here to insert a new bit. So what does this all mean? Well, there's 2 takeaways here. The first is that if we go back to the decoder, the fact that we take the memory address and decode it into word lines is the reason why, as you increase the size of a memory array, it becomes slower. It's the fundamental reason why we have a memory hierarchy, because if you make a bigger memory, you have to have more word lines. More word lines means a bigger decoder, and a bigger decoder has a longer propagation delay. So that's why the level 1 cache, which is a small RAM, is faster than level 2 cache, which is faster than level 3 cache, which is faster than level 4 cache, which is faster than the off-chip RAM. It's all has to do with it. That decoder is the reason why larger memories are slower, because larger decoders are slower, because you have to put the propagation delay to make this decoder is larger. You have to have more, the critical path in there is, the logical critical path is larger. So this is the whole explanation as to why we have a memory hierarchy. That's the first point. The second point is, notice that the DRAM requires 1 transistor per bit, whereas the SRAM requires 2 transistors plus 2 inverters, each of which require 2 transistors themselves. So there's 6 transistors here. There's 1, 2, and then there's 3, 4, 5, 6. 6 transistors. So there's 6 transistors per SRAM and 1 per DRAM. So that's why DRAM is denser. You can fit more bits in DRAM than you can in SRAM. But every time you read a DRAM, you have to replace the value in there because you discharge that capacitor every time you read it. Also, the capacitor discharges over time no matter what, so you have to refresh them periodically even if you don't read them. So DRAM has that disadvantage. But is that the only reason why DRAM is slower? Well, no. Actually, it has more to do with the fact that because DRAM is denser, you can fit more bits, which means the decoder is bigger. So it's the decoder that's really the difference in performance between SRAM and DRAM.
I could be wrong here, but the capacitor well in the silicon, actually, I think they've already hit that limit for how small they can make that.
Mm-hmm.
But like we haven't hit the limit for how small we can etch transistors.
Yeah, that could be. Yeah, that would explain why
SRAMs.
DRAMs haven't really gotten. I mean, it's kind of crazy that. I mean, what you buy a new computer now, it's going to have 32 gigs of RAM at most, 16. That's the same as we had 20 years ago, really. Yeah, so the capacity of DRAM has not improved much. Okay, I think that's the last topic until we get to the graduate project. Okay, so is any questions about that stuff? Okay, so I'm gonna go through the how many grad students do we have? Okay, so 4. Okay, so I will go through this fast. If you have any questions, any clarifications, come see me in my office, and we will send out a formal lab sheet for this. Everyone else, just give me a minute because I need to pass out the surveys. Okay, so the idea, I mentioned this last time, is we want the CPU to be faster. How do we make it faster? Well, there's really only 2 ways. Well, assuming we don't change the instruction set. What's the performance of the CPU? Number of instructions executed or dynamic instruction count, times CPI, cycles per instruction, times cycle time, right? So if we're not going to change the number of instructions, meaning we're not going to change the instruction set, because we want to use MIPS, right? We want to make that standard. We want to make it backwards compatible and all that nice stuff, right? So there's only two ways, CPI and clock. We can make the clock faster or we can decrease the CPI. So let's decrease the CPI. How do we do that? Execute 2 instructions per clock at most, right? Meaning that potentially 1/2 cycle per instruction, right? So how do we do that? We could do it dynamically or we could do it statically, meaning that we can, well, let me back up. What limits how many instructions you can execute per cycle? Data dependencies and control dependencies, right? Hazards, right? So anyway, this is a VLIW, very long instruction, where basically the idea is to pair every pair of instructions will pair together, we'll execute them at the same time, right? What happens if you can't execute them at the same time? Well, if you can't, then you put a no-op. You just have one instruction and no-op, and then it becomes the same as our old CPU, right? It operates the same. Okay, so there's a few simplifying rules that we can put in here. All instructions will be paired, so we have to take the code and transform it, so we pair up all the instructions in the program. What I mean by that is, when you dump the hex file, every pair of instructions in the hex file should be joined. So we'll essentially have 64-bit instructions. Assume we can't add another port to the data memory, but don't care because we didn't put a data memory in, so you don't have to worry about number 2. Number 3 is, I forgot to take that out. Number 3 is we can only have one branch or jump, right? Because it would be a lot more complicated to support 2 branches or jumps in the same instruction word packet, right? So only the first instruction can be a jump or branch, meaning that the program counter value of each jump or branch has to be an even number. If you put another instruction in there with it, then it will be executed regardless, or will always be executed even if the branch is taken. So it acts as a branch delay slot, right? Make sense? Okay, and then the PC will increment by 2 each time, essentially. So what that means is that the easiest way to handle that is to just cut off the least significant bit of your program counter. Okay, so it's actually not much. You don't have to do much to your instruction memory. You just make the depth, cut the depth in half, and make the width double, right? The PC is incrementing by 2, so the address that you're sending to the instruction memory is going to be 9 down to 1, or in our case 11 down to 1, right? Because we're using a 12-bit PC. And then add 2 additional read ports and 1 write port to the register file, and you add a second ALU, which I show here. So register file, you extend the ports, you add another control unit for the second instruction, and you add another ALU, and that's really all the hardware, all the major components you have to add. The high and low registers you can share. So if you have a multiply on the first or the second instruction, you can give priority to the second one. Or if you have them on both, you give priority to the second one. Okay, and then the only other thing you have to worry about is you have to potentially bypass if you write in the first instruction and you read in the second instruction, you may have to bypass that value internally in the register file. Okay, so then for the code, you'll take your code. This is the square root code. No, this is not the square root code. This is something else. It's another example code. You would take this, and what is this doing? Multiplying an array? Load, multiply. Oh yeah, it's multiplying everything by 10. Yeah, it's multiplying by 10. Load a second element. Oh, multiplying each element by 10, and then adding it to something in a second array, and then storing that back. Right. So this is an example program that's just a traditional program. And so for the VLIW, you would have to start out by adding a no-op after every instruction. And then your goal is to fill in those no-ops in a way that doesn't violate any of the rules. Now in this case, obviously we don't have load word and store word, so this is not directly applicable. But you want to pair instructions that can be performed together. And the goal is to run this on the square root code and get at least a speed up of 1.3. So you want to have at least 30% of the instruction packets not having a no-op. Make sense? I went through that super fast. Any questions? Phil? Does that make sense?
Yeah. Okay.
So once you generate the code from Mars, you can just use this sed command. It'll pair up every other instruction in the hex dump. So it'll create 64-bit instructions.
All right. This will be interesting.
Okay, I'll send the thing out tomorrow. I've got this written up in a PDF. I just have to dig it out. Okay, I think that's it. We got like 10 minutes, right? Okay, I hope you enjoyed the course. This semester, we make changes every semester. You probably heard last semester we actually didn't even have the lab component at all. This semester we came back to doing the labs. But I tried to make it more of a hybrid course where I tried to have equal parts conceptual, equal parts lab. Let me know what you thought of that on the surveys, if you like it, or if you want more lab and less conceptual, or more conceptual, less lab. Obviously, the lab part, the frustrating part of that is you have to deal with the tools, right? There's a lot of kind of just hacking at hardware designs and software, but it's more hands-on, it's more applied. The conceptual part is a little bit more kind of dry and less practical maybe. But you don't have to deal with tools, you don't have to go to the lab. It's more like a traditional course. So I'm curious what you think of that. If you'd rather this be taught more just as a, conceptual, like I did the last two lectures, or more of a lab, build a CPU and try to, or the calculator, or different types of hardware designs, and just see what you can get working in the lab. So you can write those in the comments here. Phil, do you want to distribute these for me?
Yep.
And while you're doing that, I'm going to pack up. And if you have any questions, feel free to contact us. I'll be here until